Hey everyone, welcome to the third example of static equilibrium, and in this problem we are going to be solving the angle of depression of a second rope and the tension that it must hold to keep this 60 kilogram block in place. We know the downward force of the 60 kilogram block and we need to hold it up. The downward force is going to be gravity. Gravitational force is mass times gravity, so 60 multiplied by 9.81. The downward force of this 60 kilogram block is 588.6 newtons. That's the force pulling down. The left and the right rope must be pulling up a total of 588.6, or else this 60 kilogram load would go crashing to the ground. Let's go ahead and solve the y component, that up-down component of the left rope. In order to get a y component, we take the magnitude of that force, the 500, multiply it by the sine of the angle. Recurring theme in vectors. Sine means up-down. Our y component is 383 newtons. That means the left rope is holding 383 newtons of that load. But there's 588.6. What about the other newtons? What's holding those up? It's the other rope. The right-hand rope must be holding up the rest of that load. So we can subtract it. 588.6, subtract the 383. It's going to equal 205.6. The right rope must be holding up 205.6 newtons, or else that load would go crashing down to the ground. We've got up-down balanced. Let's go ahead and solve the x component of that left rope. To get an x component, it's 500 cos the angle. Coses are your x's. Force x is going to equal, we plug this into the calculator, 321.4 newtons. If the left rope is trying to pull it 321.4 newtons to the left, the right rope must pull an equal amount, or else the block would go swinging left and right. Static equilibrium, not moving. So now we know the up component of the right rope, and we know the right component of that right rope. Yeah, you've seen this before. We're going to have to draw a right angle triangle and solve this vector. So I'll just go ahead and draw a little triangle here and get that hypotenuse. That's our rope. We can label this with our known values. We know that the x component is 321.4, and we know that the y component is 205.6, and that theta is our angle of depression. We won't forget to solve that before we're all done this problem. We can use our Pythagorean theorem. C squared equals a squared plus b squared. And we can go ahead and fill those values in. If you've been solving vectors, Pythagorean theorem, not going to be a problem for you at this point. You should be able to knock these out. We tidy this up. We get that c squared equals 145,569.32, huge number, but we square root that and get 381.5 newtons. That is the tension on our rope. But we need to know the angle of depression at which we're lowering that down. We're going to use tan of theta is equal to our opposite, 205.6, divided by our adjacent side, 321.4. We do the inverse tan in our calculator, and we get that theta equals 32.6 degrees. We don't have to convert that into a standard angle because it's just our angle of depression. It's the angle that our rope is hanging down. So we know our magnitude, we know our direction, we can finalize this and say the second rope has an angle of depression. So that's the angle that it's hanging down from some flat ceiling, and the angle of depression is going to be 32.6 degrees, and it's going to have a tension of 381.5 newtons. Ta-da! all of our forces cancel out. Yeah, we figured out this final rope. And that is the third example of static equilibrium. I hope that this was helpful. If you have any questions, leave them in the comments below, and I'll be looking forward to seeing you next time.